Hello, everyone. This is Sunshine Menezes, and I am the Executive Director of the Metcalf Institute at the University of Rhode Island's Graduate School of Oceanography. Welcome to our webinar series. This series is part of Metcalf Institute's Climate Change in the News initiative, which was designed to help journalists cover climate change and provide contacts and resources and some windows into the science of climate change to improve and expand coverage of these topics. Today, following our speaker's brief presentation, we will allow 15 to 20 minutes of time for questions and answers. And you can submit your questions at any time via Twitter using the hashtag MetcalfCC, as in Metcalf Climate Change, or you can send an email to us at webinars@metcalfinstitute.org, or of course you can submit a question using the events page on the Google Hangout itself. So right now I'd like to introduce our speaker for the day, who is Brice Loose. Brice is a marine geochemist and assistant professor here at the University of Rhode Island's Graduate School of Oceanography. He uses gases to track patterns of melting ice and also currents as they travel between polar oceans and the deep oceans. He also measures gases in seawater and in ice melt, both sea ice and glacial ice, to better understand processes both including glacial melt and air-ice-ocean gas exchange. And he will tell you more about that right now. Brice.
Hi, Sunshine. So you can see me now?
I can see you.
Great. Okay. Thanks everybody for tuning in to see this webinar. So I have slides, and I'm gonna go ahead and transition over to share those slides with you now. So you'll basically hear my voice as we go through these slides, and then at the end, when we get to the Q&A part, I'll try to come back on screen so you can see me. So all right, so I've maximized the presentation now, so hopefully everybody can see this. I'm going to focus my discussion today on Antarctica, and in particular on the West Antarctic ice sheet, which is this whole section colored in deep red that you see off to the left-hand side of the image. It's basically defined to the north by the Antarctic Peninsula, which reaches up towards Chile, and it's defined to the east by the Trans-Antarctic Mountain Range. And then an area of greatest interest to scientists because it's the one experiencing the greatest change and has the greatest potential to, in the near term, affect sea level rise. So just before I get into the details of the West Antarctic ice sheet, I want to just throw some basic statistics at you. I'm going to, the two major factors that we think about in contributing to sea level rise, at least in terms of the long-term trend, are the effect of thermal expansion from seawater, and then also sea level rise from melting glaciers, which is what I'm going to talk mostly about today. So the thermal expansion part is simply it's a consequence of the fact that as you warm up most materials, including seawater, their density becomes less and they take up a greater volume. So as seawater warms as a result of a warming planet, it will tend to raise the sea level. And in the last 40 years, we're currently already undergoing a sea level rise driven by thermal expansion, and we've experienced something like 0.6 millimeters per year during this time period. If we look forward to trying to project out what we can expect, the prediction is something like for every degree C of global average temperature, we can expect something like 0.4 meters of sea level rise. So it's going to be a significant contribution into the future, although there may be some tapering as we move farther up in the future. Now, if we compare that with melt from glaciers in the current scenario, within the last 40 years, we've experienced about double the amount of sea level rise from melting glaciers. That's about 1.2 millimeters per year. But the big question then is, how is that rate going to change over time? And considering that if we go to the extreme scenario where all of Antarctica and Greenland were to melt, we would raise the sea level by 65 meters, which is, of course, not a scenario that anybody's contemplating for the near term, but we're looking at a large reservoir. So we really want to know how this ice is going to affect sea level as time goes on. So before we continue into the processes, though, I want to make sure and just draw a few distinctions because the cryosphere is kind of a complex place. There are lots of different types of ice, and so I want to just distinguish the three major types that define the region. So sea ice is the type of ice that basically forms from seawater itself, so it's floating over the water, and it's frozen seawater. It has a salinity that's slightly less than seawater, and that's because once it forms, seawater as concentrated brine tends to drain out. And if you look at this image here, you can see these so-called brine channels where the seawater actually drains out of the ice. So the point of this is that sea ice, its formation and melt has no net effect on sea level rise because it was formed from seawater, and even on an interseasonal basis, there's no effect on sea ice. So this whole, or on sea level rise. So this whole portion of the ice map of Antarctica essentially doesn't contribute to sea level rise. What we're interested in is the land-derived ice. Now, icebergs, on the other hand, those are a very important factor in measuring the rate of sea level rise because these are basically chunks of terrestrial ice which have fallen into the sea, and they typically move away from, for example, Antarctica and melt slowly. And these are definitely a major conveyance mechanism by which the ocean rises as a result of ice mass loss. And then finally, I just want to give you a kind of a conceptual depiction of what a land-based glacier looks like, how it forms, and how it operates. So what you typically observe is that we have a gradual accumulation of snow. It's a persistent accumulation which, unlike low-latitude climates, you get snow in the wintertime and it melts in the summer. Well, it never melts in the winter at these high latitudes. And so you have this gradual accumulation snow which compacts first to firn and then to ice itself. And because this creates kind of a hump or a buildup, there's basically a slope in the surface of the ice towards the ocean edge, which is at a lower elevation. And because this is plastic, it essentially sinks under gravity, and that tends to cause a flow from the interior of the continent towards the edge. So in an ideal scenario, the rate of accumulation of snow is matched with the rate of accumulation, or with the rate of melt at the edges. And so we have an ice sheet who has a stable mass balance, and everybody's happy. And to a certain degree, that's what we've experienced, in the Anthropocene during this time period that we've been on the planet. But that's since changed, and it appears to be changing even more rapidly. So to give you an idea of what this flow looks like, this is a large ice stream from Antarctica. I think this might be the Willands ice stream. And you can see it's almost like a river of ice within the glacier itself. So it's a massive flow of ice from the center of the continent towards the interior. And so we're really interested in the rate that these things flow at, and then the stability of the structures themselves. And if we look, for example, at Antarctica and Greenland together, one of the things that we can pretty easily do from satellite is measure the flow rate of these different ice streams. And typically where we see, for example, in red, a high flow rate, which is basically these are high ice velocities along the coast of Greenland and along, particularly in the West Antarctic. These are areas that are moving quickly and also associated with negative mass balance, meaning they're losing ice over time. So the region I'm going to focus on here, of course, here's the West Antarctic ice sheet. I'll be focusing on the Amundsen Sea sector because this is the area where we're seeing the greatest disembark of ice from the continent. So we're interested in the processes that are driving that. So one really important feature in the stability of an ice stream is actually this ice tongue which forms at the end. These are known as floating ice shelves. And so this feature basically occurs when, if you imagine sort of a front of ice contacting the ocean, that ocean has more heat than the ice does, and it also is denser, so it tends to force itself underneath the ice and melt and then eventually create this cavity. So the cavity is defined by the grounding line, which is this point where the ice lifts off from the ground, and then eventually the ice shelf thins towards the edge, but a large portion of this ice shelf is actually floating under buoyant forces because it's, of course, less dense than seawater. So it's being held up, which is what allows this cantilever process. But also the seawater is actually exerting a restraining force, which I've tried to note here with the figure, which is similar to a buttress, which is why I put this picture of the buttress here. I'm sort of trying to graphically draw the parallel between the restraining force that a buttress provides to to a building and the restraining force that an ice shelf provides to the ice stream upstream of it. So this is it's an important structural feature in determining how fast the flow of ice from the interior towards the edge takes place. And what we've observed is that when these ice shelves collapse, this is an example of a very large ice shelf collapse along the Antarctic Peninsula. The ice stream that is backed up behind it tends to flow much more quickly, and so that's what this figure depicts here. Essentially, the rapid retreat of the grounding line, and then a much faster flow of the ice stream from the interior towards the edge. And so it speeds up the overall mass loss. So when a glacier experiences an ice shelf collapse, that's usually a sign that that things are changing dramatically and that things are going to speed up. It's interesting to note that at this point in time, basically all of southern Greenland has no more ice shelves. It did in the past, but they've all essentially. So now I've got this nice video that I want to share with you that was produced by the European Space Agency, and it shows a little bit more, it gives a little bit more detail and has an excellent graphical description of this particular glacier known as the Pine Island Glacier. So again, we're looking at a feature here. We're looking at the ice shelf. You can see the grounding line here towards the back, and then the ice tongue as it moves out. So the first part of the video basically just shows how this ice shelf is affected by gravity. But I want to go ahead and move ahead towards the part where they demonstrate the grounding line. So okay, so you can see here where they've identified the grounding line through radar interferometry, and this is essentially showing where the ice shelf contacts the bedrock. And what the video depicts is the extremely rapid grounding line retreat, which has taken place in the last approximately 20 years. So as you can see, we see circulation of water underneath these ice shelves, and that circulation can tend to lead to melt. There's always been circulation under floating ice shelves, but what's in it is we're observing a really rapid grounding line retreat over the past 20 years. And this can be seen again from satellite, which is what's depicted here. So these striped lines, those indicate the position of the grounding line, and they're essentially showing you how the grounding line has been walked back towards the interior of the continent, with a huge change from 2000 to 2009, and then into 2011. At this stage, the grounding line, or that is the length of the entire ice shelf, has nearly doubled in size from 30 to 60 kilometers. So this is a massive retreat. And the thing that's really worrisome about West Antarctica in particular is that the entire bedrock is being weighed down by the heavy ice that's on top of it, and all of that bedrock, essentially, to the best of our knowledge, is beneath sea level. So if you let's scoot back there a little bit, see if I can get back to that. Yeah, perfect. No. Yeah, so all of this bedrock moving back towards the interior is beneath sea level, and so there's really no shoreline for the water to encounter as it works its way underneath the ice shelf. And so when we start to examine that and the effect that it seems to be having on this whole setup, so this is the Amundsen Sea here, and you see all the major ice shelves in the Amundsen Sea identified. We've been looking at Pine Island, but all the others are there as well. When you examine that and you extrapolate backwards, there's basically no topographic feature that can be seen that would actually stem the intrusion of the seawater beneath the ice. And that was the major conclusion of this paper by Rhode et al. In 2013 that some people may have seen, basically saying that the West Antarctic ice sheet has reached a point of no return, and that there's nothing that's going to keep these ice shelves from continually being undermined. And so we're concerned that we'll start to see the collapse of the ice shelves, which will speed up the ice stream, and in general an acceleration of the ice velocity and mass loss. The rate at which all this takes place is a really open question. It's not clear, and it's even more interesting to try to consider, and in some ways more confusing to try to consider why this is all taking place in the first place. But this is, I'm going to tell you what we do know up to this point. So this is a figure of a large water mass surrounding the entire Antarctic continent known as circumpolar deep water. So this water is really old, and so we're actually looking at fields of oxygen because that's an easy way to look at it. It's low in oxygen because it's very old, and it comes from the North Atlantic. And if you compare its temperature with the temperature of surface water and of the ice sheets, it's almost 4 degrees warmer than surface water in the Antarctic, which is close to -2 degrees. This water has a mean temperature of about +2 degrees. So as heat sources go, certainly we wouldn't consider this water warm, but when it gets up onto the ice, up onto the continental shelf and it interacts with the ice, it's capable of producing quite a lot of melt. So this water mass has always been there. It's a major feature of the circulation of the ocean. And we've seen, as long as we've been taking these measurements, that this water creeps up out of the deep ocean and works its way onto the continental shelf. You can see the shelf break there. And eventually it finds its way underneath these floating ice shelves to produce melt. But what appears to be happening is that the rate of this upwelling onto the ice shelf has increased significantly in the paths leading to faster melt. So this is a really different scenario from what you experience in the north, where primarily around the Arctic, we're basically seeing melt, which is atmosphere, or we're seeing warming, which is really atmosphere derived. It's essentially centered on the fact that the atmosphere is warming, and that's warming the water, and all of that is causing the sea ice to melt away, which is producing the positive feedback. We're not seeing any of that really in the Southern Ocean. For the most part, the temperature has not increased, at least not at the same rate, and it's slightly variable by region, but there's not a clear atmospheric connection, or at least a thermal connection like there is north. What we have seen, though, is a change in the westerly wind. So that's what this picture is meant to show. This band of red and yellow is essentially the westerly jet around Antarctica, similar to our jet stream. And what we've seen is in the past 50 years, this jet has moved closer to Antarctica, so it's become tighter around the continent itself, and it's intensified in strength. And the only working theory that we have at this point for possibly bringing more of this warm water in contact with ice shelves is that it's this strengthened wind causing more upwelling. The difficulty is that when we go out and we try to model this phenomenon and draw this connection, our models at this point are not able of reproducing this feature. Often when winds are strengthened in a model, you get the opposite effect. The ice sheet actually, the continental shelf cools and ice sheet melting occurs less. So we're still trying to work on how these two features are connected, and that's an active area of research. But from here the plot also actually thickens, which I think is pretty interesting because there are also some atmospheric studies which basically connect the movement of the westerly winds to the ozone hole over the southern hemisphere, which was produced by CFCs and was thought to not really have like a climate impact, but in fact there is this climate feedback in the sense that its effect on the stratospheric air temperature is thought to have caused the westerly winds to move closer to Antarctica. And so now we're in a situation where that ozone hole is healing itself. It's projected to completely close by the middle of the century. So there's a big question, when we add the effect of ozone hole closure on top of the effect of climate change, what will the wind field look like, and what will what effect will that have on the currents around Antarctica? So it's a much more complex cascade of processes that could tend to go in any number of directions as we move into the future. And so it's really interesting, but there's still a lot to be learned about this process. So I see I'm at about a little over 16 minutes, so I'm going to go ahead and stop here. I have a few slides that describe I thought I would stop and then just go ahead and see if there are questions, and I'm happy to talk. Let's see, I'm going to stop screen sharing. Okay, I'm back, and that's essentially what I have to share, but like I said, I have some other slides. I'm also just happy to take questions.
Thanks, Brice. I guess I would encourage you to talk take some water, but talk for a couple minutes about the significance of everything you've just described for global sea level rise models. If there are still these fairly sizable uncertainties, regarding future melting. What does that mean for global sea level rise modeling?
Okay, yeah, so that's a good question. I think we're looking at a scenario where in the worst case in the worst case scenario, if you melted the West Antarctic ice sheet, you'd produce something like 1.2 meters of sea level rise. So it's not a massive amount compared to some of the other quantities that are out there. And as it is, we're the IPCC predicts something like 40 to 80 centimeters of sea level rise over the next by 2100. So we're in that time frame. I guess the question is, how much time are we going to be given to prepare? This could all happen very quickly, or it could be stretched out over the course of a century. And of course, that 1.2 meters of sea level rise is not that's not the only factor raising sea level. So that's just one component of Greenland, which is tending to lose mass even faster, and of course this thermal expansion of seawater. So we have a number of effects laying on top of each other, and the challenge is to actually know what the timing of that will be, at what rate can taper off, and will it be a gradual process? That's an open question.
Brice, sorry, we lost you there for just a second. Could you say that last thing that you were noting about that's another question?
Yeah, well, no, I was simply saying, just trying to reiterate that it's really about the time rate of change of sea level rise, how quickly these different processes will happen and how they'll add up together. And that's something that, we're going to continue to try to monitor and understand, through modeling and prediction. But at this point, I'd say it's uncertain. We're using all available tools to try to pin this feature down. I recently saw a study in Nature where they essentially used a poll, and they polled all the different experts and then took the average of the average estimate from the individual experts to predict sea level rise over the next century. So no tool is being unutilized, but we're still trying to understand how these processes work, how the glacier slides off the ice and slides off the continent, and as we start to undermine the ice shelf, how quickly will the ice stream speed up, that sort of thing.
Thanks. There's a question here that I'm not sure if you can answer this or not, but you can tell us. A question about whether there's any way to correlate increased emissions from places where they flare gas, large amounts of gas, such as in Texas, with the global emissions that we see. Can you see any signal from that?
Let's see. So they're talking about the flaring of methane, right? Which occurs, for example, I think in large quantities over the Bakken, but in other regions of the U.S. And methane has something like a 20-year atmospheric lifetime, and it's definitely a greenhouse gas. So we're it has a complex time history, and it's complicated to do the budget on methane in the atmosphere. But you can certainly see that as a significant contributor to climate change. It has something like 20 times the global warming potential of CO2. It doesn't last as long in the atmosphere as CO2, but while it's there, it does have a significant global warming potential, and then it's eventually oxidized to CO2. So at that point, then you have CO2 doing some warming. So do we see a direct connection between the melting that we're seeing around the West Antarctic ice sheet and methane? I think that we could describe that as a teleconnection. So basically, we're seeing climate change-related strengthening of the winds. That much we think we know, and certainly methane as well as CO2 are likely to be contributors to that. That's about as closely as I can connect the two.
Okay, fair enough. I wondered if you could say, just to underscore this issue, a little bit more about the connection between the ozone hole and these climate change effects, because this is one of those things that often people conflate, ozone hole issues and climate change issues, but it just so happens that this is a part of the world where they're connected. So I'd love it if you could just say a little bit more about that.
Right. Okay. So so we know that in the 80s it was identified that we were emitting these fluorofluorocarbons, these compounds that essentially have a really long lifetime in the atmosphere. They get up into the stratosphere, and in the stratosphere, which is the highest part of the one of the higher parts of the atmosphere, they tend to impede the production of ozone, and that's what led to this ozone hole, which then basically essentially had the effect of reducing our protection from cosmic radiation that comes in from the sun. So, we were concerned about, at the time, the immediate concern was, do we really want this high energy radiation, the kind of radiation that causes cataracts in sheep and potentially cancer in people? Do we want to lose our protective blanket from this radiation? And so it was one of the major success stories of the 20th century environmental movement, in that a really quick solution was brought to bear. We rapidly reduced the emissions of these gases, and now the ozone hole is closing because all those gases are declining in the atmosphere. So that's basically, that's certainly, in terms of its ability for us to build a habitable planet or maintain a habitable planet, it's critical. It's simply, that part of it is not a climate change scenario, so it doesn't have, that part of it doesn't have a direct impact on the weather or climate that we experience on a daily basis. It's more, human health effects and organismal health effects, and what happens when you have this high energy radiation coming in. However, since that time, it's been shown that the production or destruction of ozone in the atmosphere has an effect on the temperature of the stratosphere, and so does CO2. And there is a return flow, which I only loosely understand, by which the temperature of the stratosphere can actually affect the lineup of these of high pressure systems, of weather systems, and of wind around Antarctica. And up until this point, that the cooling of the stratosphere that took place as a result of ozone destruction seems to have led to this intensification of, or this migration of the westerly wind pattern towards Antarctica. So it's this complex cascade of processes, which is still, again, it's been formulated in climate models. It's a working theory. It's not the only working theory as to why this wind intensification is taking place. So it's a secondary effect, but it is a projection of the ozone problem onto the climate problem, which is very interesting.
Okay, great, thank you. Another question that I have for you is, I'm wondering if you could talk a little bit about your lab's work with gas tracers specifically, and explain, the kinds of tools you use and the questions you are asking and how you answer them.
Sure. So maybe I'll go back to the screen share and share a few slides on those topics, because I have a few slides that might be relevant to that. So let's see here. So okay, so I use a suite of chemical tracers, namely the noble gases. So these are gases which are inert in the atmosphere. They basically don't react with anything, and they include helium, neon, argon, krypton, and xenon. Excuse me. We don't use radon for this process, but the others that we do use, and in particular, isotopes of helium are particularly valuable for this work. Helium has two isotopes: a light isotope, which is helium-3, and then a heavier, which is helium-4. So what we found is that basically, as glaciers form, from snow, you get this trapping of air in the glacial ice, which is what's meant to be depicted here. So this glacial ice has air similar to the air content that the atmosphere had at the time that it was formed. And then when this ice is melted, often at a lot of pressure, which is beneath the base of these ice shelves, all of this air is forced into solution in the water. So it doesn't bubble up, but instead becomes part of the solution of the seawater. And so that produces a huge signal in these noble gases, helium, neon, argon, krypton, and xenon. And we can see that signal, and consequently we can basically we can see meltwater inside seawater. So we can trace its pathway, we can measure the quantity of meltwater that's there, and we can essentially map its distribution from its origination point, which is the ice shelf, off into the coastal ocean. So that, in combination with the fact that we can also observe, so this is the plot that I'll explain in just a second, we can also observe with helium-3 a really strong signal of this warm circumpolar deep water, which is highlighted here. It's projected on this color axis here. So if we compare it with the other major water masses, which are all essentially zero in this helium-3 isotope, we have a huge range of dynamic range in terms of our ability to observe this circumpolar deep water. So essentially we have these tracer tools, two perfect tools for studying these processes of warm deep water creeping in underneath the ice shelf and the meltwater that is produced as a result. So what we need to do as oceanographers in order to be able to try to understand how the water gets up onto the shelf, and then what happens to the glacial meltwater as it moves off, and how the whole system basically restructures itself from the process of this circulation. We now have these excellent geochemical tools in order to be able to trace that water. You could do a certain degree of this tracing from using temperature and salinity itself, but that's a really tricky thing to do because, of course, take temperature, there are many heat sources and sinks besides just ice and the warm water. So it's kind of an ambiguous tracer. And if you take salinity, well, salinity also is affected by sea ice, which has nothing to do with this process. It's also affected by snow and other precipitation as well as evaporation. So those two tools are useful, but they don't quite get us there to being able to trace these water masses. So what you can essentially see in this figure is using, for example, neon. It has this really elevated signature in glacial meltwater, so we can see this large spike in neon and very far away at very dilute concentrations of glacial meltwater. So that allows us to map the distribution of meltwater. And like I said, with this warm deep water, we can also trace that. So we know how much is not only getting up onto the shelf, but how much is actually possibly just ventilated to the atmosphere where it loses its heat, or how much actually creeps underneath the ice shelf and produces melting. And what's the pathway that those tracers, that those water masses take? This is a picture of the Amundsen Sea, again, just oriented differently. The gray shows these different ice shelves here all along the Amundsen Sea, which are in this melting process. So we've been focused on sampling in these areas to try to be able to determine the path, not just of the ice shelf water, which is indicated in blue, this glacial meltwater, where it leaves from, but also the path of the circumpolar deep water, how it comes up onto the shelf. It tends to follow topography, but it's still not clear exactly what the siphon effect is that's bringing it up onto the shelf. And it's possible that as we stratify the system more by producing more fresh water at the surface, we're tending to trap that heat, to keep this circumpolar deep water from mixing up to the surface. So these are all questions that we can try to answer by using these tracer fields and then combining those with physical models of the region. The idea being that if the model can reproduce the tracer fields using a certain number of processes, then we're making progress towards understanding how this whole system works. So that's my small part in this very big effort to understand how these ice sheets work and to monitor them over time. So I will go back off screen sharing. And yeah.
Okay, thanks, Brice.
Mm-hmm.
I'm just checking right now to see if there are any more questions. And there's one more question here that is, again, about emissions, and this is now looking from space. Do you know if there are any new technologies to map emissions hotspots by satellite?
Yes, so there is a pretty exciting project that is getting off the ground, I think, for the second time. Unfortunately, it was supposed to be off the ground already, and it had an unfortunate incident during the rocket launch, but it's going to be called the Orbiting Carbon Observatory, or OCO, and this is a NASA project, which I think you can find much more information about if you go to the nasa.gov website. But essentially what this tool will be able to do is it'll be able to measure the total column inventory of carbon dioxide from the land surface up to the top of the atmosphere. So we'll have one single measurement of the entire column, atmospheric column, and the total CO2 in that. So yes, from the standpoint of mapping emission sources, certainly we'll be able to have these, essentially be able to make maps of areas, high resolution that have large emissions. So I would, for example, expect that we'll be able to see the features of the Bakken oil field. We should be able to see the Northeast, at least to the degree that it's still using some coal for power plant production. We may be able to really pick out features around cities. It's also really valuable because it helps scientists by giving them a lot more data for these large-scale inversions that basically help them try to parse out the carbon budget between the atmosphere, the biosphere, which is all the plants that grow on land, and then the ocean, because those three essentially work in concert with each other to divvy up the total amount of carbon, both human-derived and naturally derived. And so as we try to figure out how those sources and things change, we need more information, more spatial detail, and it should help with that. So for example, over a region of the ocean which is taking up a lot of CO2, in principle this OCO satellite should see a decrease in the column inventory of CO2, indicating that that CO2 is being consumed by the ocean. That's the only one that I'm aware of at this time.
Okay, great. Well, thank you very much, Brice, for your time today. We're really glad to have featured you.
My pleasure.
And I would also like to thank all of you who joined us today for the webinar. And please mark your calendars for tomorrow, because we'll be doing a second webinar tomorrow featuring Katie Arkema from Stanford University and the Natural Capital Project. Katie will be talking about the role of coastal ecosystems in protecting from the increasing strength and/or frequency of big storms affecting coastal communities. So tune in tomorrow, same time, 1 p.m. Eastern, and you can also submit your questions via Metcalf CC on Twitter or by email or by Google+. And we look forward to seeing you then. Thanks again, Brice.
Thanks, Sunshine. Have a good afternoon.